Hello everyone, this is Sarvesh, lecturer in Civil Engineering, Government Polytechnic, Station Bangalore. And the course is Reinforced Concrete Structures. And this is a continuation to the previous lecture, that is design of continuous beams and slabs by limit state method as per IS 456-2000. After completion of this lecture, you are able to know how to design a continuous beam by limit state method as per IS 456-2000. So in this lecture, we are going to solve a design example problem for better understanding. So we will discuss how to determine the dimensions of the member, effective span calculations, and loads, how to determine the loads and the bending moment and shear force coefficients. Then how to determine the area of steel and design of shear reinforcement, and we will check for deflection. So in detail, we will solve example problem. Okay. And before going to the today's lecture, so just recap what we were discussed in last class. In last class, we were discussed about the design procedure of continuous beams. That means how to design the continuous beams as per IS 456-2000, and how to use the bending moment and shear force coefficients for determining the bending moment and shear forces in continuous beams as per IS 456-2000. And we were discussed about the uh, how to design the shear reinforcement for continuous beams and how to check the shears. And at last, we were discussed about the check for stiffness. That means how to check the stiffness as per IS 456-2000, right? So all these limitations as well as the specifications, guidelines which are provided by the IS 456-2000, we were discussed in last class. And based on the procedure, I would like to solve an example problem. So this is the problem. So design a three-span continuous beam has end span of 4 meters and interior span of 3.5 meters. The width of support is 300 mm. The ends of the beam are simply supported and it carries a live load of 8 kN per meter and dead load of 10 kN per meter, and this is excluding the self-redundancy. Use M20 grade concrete and Fe415 steel. So design a beam for texture. So that means based upon this given data, I just drawn a diagram here. So this is the three spans. Here it says minus spans and here span. So continuous beam has end span of 4 meters. That means these are two are end spans, and an interior span of 40.5 meters, right? So this is the interior, right? So this is 4 meters, this is 4 meters, and this one is 3.5. And the width of the support, that means here we take this one, and this is a width of the support, that is 300 mm. It is very important in continuous beam for determining the effective length of this one, right? And the ends are simply supported and it carries a live load of 8 kN per meter and a dead load of 10 kN per meter, right? So this is the data given in the problem. Now before going to calculate, so what is the first step? First first thing is you need to check whether the IS 456-2000 proposed a method, that means to determine the shear forces and bending moment. The code is proposed to some coefficients in IS 456-2000, and that coefficients are used to determine the shear force and bending moment. But there are certain limitations for using that coefficient. The limitations are, first one is it should have minimum 3 spans. That is first limitation. Second one is the beam or slab should consist only UDLs. And third one is the difference between the any two spans should not be greater than the 15% of the longest span, right? So here the longest span, if you observe from here, the longest span is this 4 meters, and you need to check. So first criteria is so minimum 3 spans, so it is satisfied. Second condition is it should consist only UDS, that means 8 km per meter and 10 km per meter, satisfied. Next one is the difference between any two spans should not be greater than 15% of the longest span. So longest span is this one. This is the longest span. The difference between these two, any two, you can take it and find out the difference. So here, so the difference is 4 minus 3.5 is 0.5 meter, and 15% of the longest span, that means 4 15 4 meters in 4 meters. What is the 15%? That is difference of the difference between these span is 4.5 by 4 into 100 will get 12.5%, and this is less than the 15% of the longest span. So therefore it is satisfied in all three limitations. So you can use the IS 456-2000 coefficients for determining the shear forces and bending, right? So next is, so here we have checked and it is satisfied. So then go for calculation of dimensions of the beam. So as I told in last class, first you need to assume the dimensions of the member based on the thickness ratio, right? So here I am assuming the overall depth of the beam is L by 12, right? So therefore overall depth is equal to 4000 by 12, get 333.3 mm, and assume B is equal to 250. Right? You can assume any value, right? And assume 20 mm diameter of bars and clear cover to reinforcement as per IS code. It is 25 mm per beam. So therefore calculate the effective depth of the beam, that is 335 the overall depth minus 25 is the clear cover minus 20 mm is the diameter of the bar, so 5 by 2. Okay. So we will get the total value is 300 mm. This is the effective depth of the beam, right? So you can assume directly, you can assume effective cover directly, no need to assume clear cover separately or diameter of the bars. So simply I assumed in different way, doesn't mean that you need to follow only this. You can assume here also, you can directly assume that L by 12 is the effective depth and assume effective cover is, let us say, 50 or 48 and calculate the overall. So any either way you can determine it. There is no certain fixed rules, right? It's a flexible. You can assume anyone because see, the starting we don't know the values, so we are assuming the value. Then we will check whether these dimensions are suitable for our member or not, right? So, right, okay. So here the effective depth is 300 mm. Overall depth is 335 mm. Then you go to next step. After calculation of this one, you need to calculate the loads on them. And before that, you need to calculate the effective span, right? So the effective span should be calculated based upon the what is that the width of the span. So there is another condition for calculation of effective span. If the width of the span is less than the 12 times the uh, clear span, right? If the width of the support is less than the 12 times the clear span, then you can calculate the effective span same as your simply supported. If it is greater than, then another two cases will come. So you need to check whether it is less than or greater than. So here the clear span by 12 is 333.3. So our width of the support is 238. So it is less than the L by 12. Therefore, you can calculate the effective span is least of the following. That is center to center distance between the supports or clear span plus effective depth. Whichever is less, that will be considered as your effective span. Right. So the center to center distance is 4 plus 3.3. You get 4 point, right? Wait. Yeah, width of the support is 4. Right. Next is so this is 4 plus 0.3 with 4.3 and clear span plus this is width of the support is 300, right? So 300 less than 300. So clear span plus effective depth, clear span plus effective depth, the effective depth we got 300, so it is also part 4, so we get effective, hence effective end span is 4.3. So here one more thing you should remember, here we have three spans and three spans the distance is different. This is 4 meters, this is 4 meters and so you need to calculate the effective span separately for end spans and interior span, right? So here we have calculated for end span. Similarly, you should calculate for interior span. That is center to center distance. That is 3.5 plus 0.3, 3.8, and clear span plus effective depth 5.3.8. So the effective interior span is 3.8 meters, right? So next is calculation of loads. Here, the self weight of the beam is overall depth into width into 25 is the unit weight of RCC and per meter length. So that will come as 2.094 kilometer meter. Dead load WUD equal to 10 kilonewton per meter and total dead load is 10 plus 2.094 12.094 kilonewton. Right. And factored dead load. So the factored dead load should be calculated by application of partial safety factor, that is 1.5 as per IS 456%. So therefore it will become as 18.141 kilometer per meter. And imposed load, that is 8 kilometer per meter, and the factored imposed load can be calculated by applying the partial safety factor, that is 1.5 12 kilometer per meter. So dead load is fixed, right? So next is, so you have calculated the factor loads. Next we need to determine the bending moment. So if you so for calculation of bending moment, we need to determine the bending moment coefficients as per IS 450-60% per continuous beams. So therefore, here you need to calculate the span moments and design moments separately, right? Span moments and support moments. So here the span moments is near middle of end support at middle of interior span. Edge support next to the end support and edge interior support. So corresponding values you can take it and determine the bending coefficient, and based upon that calculate the bending. So here first maximum negative bending. So negative bending moment occurs at the support, other interior supports, or at the support next to the end support, out of which I have calculated the maximum. So because before going to calculate the bending moments for all the cases, now before that I need to check whether whatever the dimensions I have assumed, whether those dimensions are satisfying or not, or those dimensions are sufficient to resist the bending moment which is developed with the beam. That I need to check before going to calculate all the bending moments and reinforcement. So for that, generally what we can do is in practical, we should calculate all the bending moments separately by taking the corresponding coefficients, and out of which we have to take the maximum one. And for that maximum one, we need to check the dimensions. So here, due to the time constraints, I am directly taking the maximum bending moment. So as I told earlier classes, from this coefficients you can easily identify where you will get the maximum bending moment. That means the loads are constant, effective lengths are constant. The only changes is coefficient. So where you will get the maximum coefficients, at that place you will get the maximum bending moment. So from the table you can observe where you will get the maximum bending moment. This is positive. So in positive, maximum you will get for this case, and in negative, maximum you will get for this case. And compare these two. So out of these two, you will get maximum in this case. So what is this one? This is edge support next to the end support. That is negative bending. So that is why I directly calculated the maximum negative bending, right? So the maximum negative bending moment coefficients are taken, and which is occur at support next to the end support, right? That means maximum negative bending. So here WUD square by 10 is plus WL square by 9. Substitute the values. That is 18.141 into 4.3 square by 10. 12 into 4.3 square by 9 will get 58.2 kilonewton meters. Right? This is the maximum negative bending. And to resist this much of bending moment, what is the depth required? That you need to check, and this should be checked corresponding to the MU limit. That is the bending moment corresponding to the balance section, right? So that can be determined based upon the depth of neutral axis. So maximum limiting depth of neutral axis. That is XU max. That XU max can be calculated as per IS 456-2000, and that is based on the grade of steel. So for FE 415, the MU max is equal to 0.138 epoxy K into BD square, right? So from this should be equal to this bending moment, and here the unknown is FCK is known, B is known, but D is unknown. Remember, don't substitute whatever the effective depth we were derived in first case, right? So here we are going to calculate the effective depth required to resist this much of bending moment, because this is the maximum bending moment. If this depth required is sufficient to resist this much of bending moment, obviously, so because we are calculating corresponding to maximum bending moment, so that means if it is safe in maximum bending moment, so in all other cases it is less than the maximum. That means it is obviously safe. It is safe in maximum case, that is safe. Obviously, it will become safe in other cases, because in other cases the bending moment is less than the maximum, right? So So this maximum bending moment equal to mu max, that is 0.18 AD square, right? So substitute the values and determine the D required, right? So here, uh, here D required, I got it as 290.4 mm. So therefore, uh, then you need this much of depth required to resist this much of bending. But what we provided, the effective depth provided is 300, right? That means uh, D required is less than the D provided. That means it is safe. So you can proceed for further steps, right? So therefore, overall depth is this is fine. So hence, provide overall depth is what is effective depth provided is 300, right? And 335. So here we are providing overall depth is 350 mm. Why? Yeah, because 335 is required is 335, so we are changing into 350. So what is this? Yeah, why? Because 335 seems to be a little bit odd, so that is why I am making into 350 as overall depth. So again, you need to calculate the loads based upon your because the self weight will change. So based upon that, you can calculate the loads, and again you need to check for no need to check because only small changes and the effective span will change. Effective span of for interior spans, right? So for interior spans, you need to calculate the effective span for interior span, that is rear span plus 2 into width of support by 2. So it came as 3.8. And effective span for end panels, it is rear span plus 2 into width of the support by 2 is 4.3. So for that, you need to calculate the positive bending moment near the middle of end span. So the positive bending, maximum positive bending moment, that is 18.8 4.3 square by 12 plus 12 into 4.3 square by 10. This is 50.354 km/meter. And this is bending moment. This is near the middle of the span and near the middle of interior span. Interior span, the span is 3.8 meters square. So 18.28 into 3.8 square by 16 plus 12 into 3.8 square by 12 into 30.938 kilometer meters. So out of which maximum is near the middle of end span, that is 50.354 kilometer meter. That is the maximum positive bending moment. Now the bending moment at support equal to end support equal to 0. So the bending moment at next to end support, that is uh, next to end support, you have to take the half of the for this span. This is the three spans. So bending moment at support next to the end support, that means at this place. So bending moment, 50% of the bending will come from this span and 50% of the bending moment will come from this span, right? So that is this is WL square by 12. The coefficients is same, but load will change. Load and span distance. That is what 50% half of this one plus half of this one. So that we get it as 52.5 0.051 kilonewton meter. This is the bending moment at support next to the end support, right? So like this, you have to determine the bending moments for all the cases, for all the moments, that is span moments as well as support, right? So next is at middle of end span, that is P and G. Sorry. So next you need to determine the calculation of area of steel. So after determining all the bending moments, then you need to determine the area of steel. So area of steel should be calculated by equating your bending moment, that is maximum bending for all bending moments you need to calculate separately. So bending moment into tensile tension force into lever arm, right? Lever arm is nothing but D minus 0.42 XU. And remember that XU should be calculated by equating compressive force equal to tension force, right? And that compressive force equal to tension force, XU will become 0.87 f of y into A of ST by 0.36 FCK into B. And here XU is unknown, right? And A of ST is also unknown. So that is why I would like to write down XU in terms of AST. So this equation is substituted here. And if you simplify this compressive force into lever, the overall equation, simplified equation will be like this. So from this equation, everything is known except A of ST. So determine the area of steel required, right, wherever you want. So first I would like to calculate the reinforcement at middle of end span. So at the middle of end span, the bending moment is 50.354 kilometers. So the reinforcement required at the middle of end span, that is 50.35 into is equal to this equation. From this equation, you will get it as from this equation you will get it as the area of ST required is 482 square, and area of steel at middle of interior span, that is at F. So the bending moment at F is 30.938 kilometer meter. So use same equation, but the bending moment is different. So for this, the reinforcement required at middle of interior span is 291 mm square. So like this, you have to determine the steel required at each point separately, right? Next is the area of steel required at the middle of interior span. Similarly, from this, got that is moment is 52.052 into 10 power 6 power 6, and if you substitute the values, and you will get 497.07 mm square. And all these reinforcement should be checked for maximum as well as minimum reinforcement, right? So as per IS 456-2000, the minimum reinforcement minimum tensile steel is 0.85 T into T by 5. So from this equation, if you substitute the values, you get 153.61 mm square, right? From this equation, you can determine the minimum area of steel required. So our whatever the area of steel we calculated, that is greater than this value. So it is okay. Similarly, we need to check for maximum also. So it is same, right? So therefore, you can assume the diameter of the bars, and according to the area of steel required, you just calculate the number of bars required for each place. So that means the number of bars required for E and G. What is E and G? Uh, EG are the EG. That means at the middle of end span. F is interior span, right? A, B, C, E are supports. So G, GU, right? So the five numbers 12 dia bars are required at E and G. That means at the middle of end span. So therefore AST is 565 mm. And at F, that means at the middle of interior span, required three numbers of 12 dia bars. So therefore the total area of steel is 339.29 mm². And B and C, that means at the supports B and C. At the supports, we required 4 bars, 12 mm dia bars, 4 12 mm dia bars, right? The total area of steel is 565 mm². So this is how you need to determine the area of steel required in tension zone for different places. That means middle spans as well as supports, right? Next is check for stiffness, right? So for checking for stiffness, uh, for continuous beams, the span to effective depth ratio is 26 into modification factor. And this modification factor is depends upon the area of steel provided in tension zone, percentage of steel provided in tension zone, right? And f of s value. That f of s is nothing but 0.56 into f of y into area of steel required by area of steel provided. From the diagram, from IS 460,000, from this diagram, from this graph, you can determine the modification factor, right? So before that, you need to calculate the tension reinforcement, percentage of tension reinforcement, and f of s. F of s is nothing but 0.58 f of y into area of steel required area of steel provided. Let me check. So the steel percentage of steel provided in tension zone maximum is 565 into 105. That is AST into BD. AST by BD into 100. Right? If you substitute the values, the percentage of steel is 0.75. 0.75 percentage. And F of S is AST required by AST provided into F of Y into 0.5, which is 205.34 newtons per mm². Then go to the graph 0.75 and 205, right? So just 0.75 means this is 0.0, 0.4, that means this is 0.2, this is 0.8, this is 0.6. If this is 0.6, this is 0.8, and this middle you will get 0.7. And 0.75 means somewhere else here. 205 means it is approximately somewhere else here. Some more. Right? If you draw the line, vertical line, projected, and approximately if you draw the horizontal line somewhere else here. Right, so it is approximately, I can say it is near to 1.3 because this is 1.2, 1.6 will be 1.4. So approximately you will get 1.3. So the modification factor got it as 1.3. So then calculate the allowable stiffness value, that means L effective by T ratio. Allowable value is 26 into 1.3. 26 into 1.3, you will get 127.7, not mm, is the ratio effective by sorry, is effective depth required. Or you can calculate L by D is equal to 26 into 1.3. So here 4000 by 26 into 1.3 will be 127.2, right? And calculate what is the actual L effective by D ratio. What is the actual L effective by D ratio? That is 4000 by, you need to calculate 4000 by effective depth is 300. So how much you got it? I have to calculate it somewhere else. Right. Let me check once, whether it is satisfied or not. Let me check. That is L effective. We got it as 4000 by 300. So it is getting 13.33. So whatever this 1000 by 26 into 1.3, sorry, 4000 divided by 26 into 1.3. It is 199 approximately. And whatever we got, it is 4000 by 300. That is 13.3. 13.3. So it is much less than the allowable value. So therefore it is safe, right? So it is safe due to stiffness. Next is design of shear reinforcement. So first we need to check whether it is safe in shear or not. So first we need to calculate the factored shear force. So the factor shear forces can be calculated from the table that is as per IS 2000. So here also you need to calculate the shear force at each point, right? So for end support and edge support next to the end support, this can be, so this can be calculated based upon the factors, right? So shear force at end support, that is factors is 0.4 and 0.45. So you will get the shear force is 54.6 kilonewton. Right? This is the shear force at the end support. And nominal shear stress, that is Vu by Bd. What is Vu by Bd? So nominal shear stress at end support, that is at A, that is Vu by Bd. So that we get as 0.729 Newton per m square. As per the AS 450,000, nominal shear stress should be calculated from this formula. Right? So this is 0.729 Newton per m square. Then you need to calculate the tau c, that is the shear resistance of the concrete, and tau c max, the maximum shear resistance of the concrete. Right? So the percentage of steel at end span, because we are calculating the shear stress, shear force at end span, at the end support. So based upon that, you need to calculate the percentage of steel corresponding to end support. So that is 0.643%. That is A by B. And corresponding to this value, you need to go to the table, and corresponding to the grade of concrete and percentage of steel, calculate the tau c value. So my percentage of steel is 0.643. 0.643, that means it will be laid between these two, 0.5 and 0.75, and this is in between this value 0.48 and 0.5 per m28 count. So based upon those values, you can calculate the interpolate the values by using this equation. So from this tau c equal to 0.5 Newton per mm square. And this tau c, whatever this tau p we got it as, tau b is 0.7 and tau c is 0.5, and it is less than the nominal shear stress. 0.5 is less than the, hence the section is to be designed for shear, right? So therefore you need to design the shear reinforcement. So for this you need to assume whether you want to provide the vertical stirrups or inclined stirrups, and based upon that you need to calculate the space. So first we need to calculate the VUS, that is the shear strength. That is VUS is equal to so just I would like to write it. So VUS equal to U minus tau C into BD. Right. From this you need to calculate the values, that is tau V I got it as 0.5 into V is equal to 250 into V is equal to 300. So I got it as 37.5. So VUC is equal to 37.5 kilometers, right? So for this 37.5, I have to calculate the this is VU, and what is this value? That is VU. VU I got it as how much? 54. So 54 minus 37.5, you get 16.5 is the VUS. So VUS is equal to 16.5. So for this, I have to design the shear reinforcement. So therefore, you can assume the calculate the SP value based upon this, right? So from this calculated the spacing, yes, I have assumed 8 mm there, 2 leg vertical stirrups. So corresponding to that vertical stirrups, I have calculated the spacing. So I required 1100 mm, right? But as per IS 456-2000, the maximum spacing between the stirrups should not be greater than 0.75D, which is the vertical stirrups, and 300 mm, whichever is less. So from this maximum spacing, you need to calculate the. So here you have key spacing, that is 1100 as per the resistance, 0.75 that is 255 mm, and 300. So out of this, which one is minimum? 8 provide 8 mm dia bars, 2 leg stirrups at 225 mm center to center. This is at the end support, right? So like this, you have to design the shear reinforcement. And similarly, you need to calculate the shear reinforcement at outer side of the support next to the end support. So for this, you need to calculate the shear force at outer side of the support next to the end support. That is 0.6 WB plus 0.6 WB. Yeah. From this, the shear force recorded at 78.07 kilometers. And then again, the nominal shear stress is VU by VD, right? So from this 1.041 Newton per mm square, and the percentage of tension reinforcement at support next to the end support is 0.643%. So same value we will get it, that is 0.52. So it is less than this one. Therefore, we need to design the shear reinforcement. Again, you can assume the spacing. So for this, I got it as 278.77 mm, and here also I am providing the vertical syrups. Therefore, the maximum spacing is should not be greater than 0.75D or 300 mm, whichever is less, right? So therefore, this is 278 as per the calculation, and 0.75 is 25. So therefore, provide 8 mm diapass 2-layered syrups at 225 mm center to center spacing. So like this, you need to determine the shear forces and shear force shear reinforcement should be designed, right? So therefore, hence provide 8 mm there 2-legged stirrups at 225 mm center to center in the span of PC. Since both the span stirrup spacing is equal, hence provide 8 mm there 2-legged vertical stirrups 225 mm center to center throughout the both the span, that is AB and AC. So this is how you need to design your continuous beam, right? So after designing, you need to draw the diagram. I hope it is not clear, but you need to draw the total reinforcement details like this. And at each section, you need to draw separate the reinforcement details for here, right? So this is how today just I'm concluding this class. So just summarizing what we were discussing because it is too lengthy problems. That is why some steps are skipped it, but 80%, 80 to 90% steps are covered in this problem. So due to the time constraint, I have skipped some steps because it is a repetition. But the same procedure you can use it for other cases also, and you can design it. So just summarize what we were discussed. So today we have solved a design continuous field. Continuous field has been designed based upon given data. And the first is we have calculated we have checked whether the given problem is suitable for application of IS 46000 method or not. That means whether the coefficients given in table number 12 and 13 are can be applicable for the present case. So that means we have checked it. That means three conditions: minimum 3 span, to real loads only, and the difference between any two span should not be greater than 15%. So all these conditions satisfied. Then we have determined the dimensions of the member. Then we have calculated the effective span for any span as well as interior span. And based upon that, we have calculated the loads. And then we were determined the bending moment coefficients. So before that, first we have calculated the maximum bending moment. That is, we got it at the support next to any support, that means negative bending moment. Corresponding to that, we were checked our dimensions. That means depth required is calculated, and our depth required is less than the depth provided, and it is safe. Then we have calculated the bending moments, span moments for all span moments and for all support moments separate. Right. So after that, we have calculated the reinforcement required for span moments as well as for end moments separate, support moments separate. Right. And after that, we have checked our beam in thickness. That means our L effective by D ratio is within the permissible limits or not. So we got safe. Then we have designed for shear reinforcement. That means the shear forces separate the supports next to the support and the other interior supports and end supports also. Right. So we have calculated the shear force corresponding to the uh, coefficients given in table number 13. and calculated the nominal shear stress, that is U by PD, and we have calculated the tau C based upon the C provided, percentage of C provided, and the grade of it. And we will compare, that means tau B is less than tau C or not. So here we got tau B is greater than tau C, and tau B is less than tau C max. Therefore, it is you need to design the shear reinforcement. So based upon that, we have calculated the base value, and corresponding to that, we have calculated the phase by ensuring the vertical stirrups with the two legs, right? And at the end, we have drawn the reinforcement detail. So this is how we need to design a continuous piece, right? So for this, I would like to conclude this class. Thank you.